Very good. So we're going to open up a new topic that involves particular solutions as well. So guys, here we have a nice classification. Please list these down. It's important. We're going to follow with these classifications as we go through 4.4. So what we learned so far is that what if we only have a homogeneous linear differential equation with constant coefficients? So here we are on 4.4, particular solution. In general, if we have a linear differential equation like an, the nth derivative of y, plus an minus 1, the nth minus 1 derivative of y, plus a1 y prime plus a sub 0 y equal to g of x. Non-homogeneous linear differential equations. What are we going to do? We're going to do two things. First of all, we're going to form a homogeneous differential equation by setting gx equal to 0. So we're going to write it as an, the nth derivative of y, plus the rest of the terms, a1 y prime plus a sub 0 y equal to 0. Then use y equals to e to mx to solve for this homogeneous differential equation. We say that, hey, we are finding the complementary solution, the complementary function. So this gives us the complementary solution y sub c. After finding the complementary solution for this homogeneous differential equation, we're going to work with g of x to find the particular solution. Work with g of x to find the particular solutions. Y sub p. After finding y sub c and y sub c, then add them together to write the general solution for the differential equation. At the end, y is yc plus y sub p. In 4.1, 4.2, 4.3, we went over different techniques to find y sub c. In 4.4, we're just going to focus on g of x. Very good. So if your g of x, this is what we're going to discuss. It's a long list. You need to know all of them. If g of x is a constant, then the particular solution is a constant. If you have a differential equation and g of x is a linear expression, then the particular solution is ax plus b. If g of x is quadratic form, y sub p is a x squared plus bx plus c. If g of x is cubic, then the particular solution is cubic, ax cubed plus bx squared plus cx plus d. So in general, if it's in polynomial form, you can say that, hey, I'm going to have a polynomial eventually available there. If it's in trig format, if your g of x is equal to, let's say, sine of, let us use something like bx, or g of x is cosine bx, then your yp, the particular solution, has general form, the combination of, let's write it down, c1 sine of bx plus c2 cosine bx. Next category, if it is e to power some exponents. If gx is e to power, for example, ax, then your particular solution is a constant like, for example, c e to power ax, this guy here. The next category, if you have a linear expression times e to power ax, if you have g of x equals to, if you have, for example, a linear expression, let me write it in the parentheses, linear expression e to power ax, then yp has the general form bx plus c e to power ax. Well, if it is in the form of a quadratic expression, if gx is quadratic times e to ax, then yp, as you guessed, is going to be ex squared plus cx plus d e to power ax. You need to remember all of these classifications. Well, the next one, if you have the combination of sine or cosine for e to power 3x, well, if we have gx as e to, for example, ax sine of bx, yp becomes c1 e to ax sine bx plus c2 e to ax cosine bx. Let's see what else left. Okay, if you have a linear expression, exponential, and cosine. Linear expression, exponential, and sine or cosine. If g of x is a linear expression, e to ax, sine or cosine. E to ax, for example, cosine bx, it's going to be then yp, or the particular solution is c1, and you get, for example, cx plus d e to ax cosine bx or sine bx, it doesn't matter which one comes first. The order is not important, plus c2, then ex plus f e to ax cosine bx. Based on how g is defined, we can construct the particular solution. Then we can plug that into the differential equation and solve for these missing coefficients. Okay, give us example. Very well. I'm going to leave that there. I'm going to use that list until you feel comfortable about it. So this example says, solve the following differential equation. Example, solve. Here we have the second derivative of y plus 4y prime minus 2y equals to 2x squared, okay, minus 3x plus 6. 3x plus 6. So as you can see, you have a non-homogeneous second order linear differential equations with constant coefficients. This is a second order linear non-homogeneous differential equation. So first you need to find the complementary function, complementary solution. So find y sub c first. So what are we going to do? We're going to just focus on the homogeneous part. Set this as a homogeneous differential equation. Well, the second derivative of y plus 4y prime minus 2y is equal to 0. Well, we have constant coefficients. A possible solution is y e to mx. We need to form the auxiliary or characteristic equation. So we get m squared e to mx plus 4m e to mx minus 2 e to mx equal to 0. This is a possible solution. So if you factor out e to mx, you get m squared plus 4m minus 2 equal to 0. E to mx is not 0, so we're going to set this equation equal to 0. M is negative b plus minus square root of b squared minus 4ac divided by 2a. So m becomes, very good, negative 4 plus minus, here we have 24. So we get 4 square root of 6. Let me see. Two square root of 6 divided by 2. So m becomes negative 2 plus minus square root of 6. So as you can see, you have two distinct solutions. yc is equal to c1 e2 negative 2 plus square root of 6 times x plus c2 e2 negative 2 minus square root of 6x. So we found a complementary function or the complementary solution for the homogeneous differential equation. So to solve this differential equation, note that it's non-homogeneous. To solve this differential equation, first we turn it into a homogeneous differential equation and solve for the homogeneous part. Now we have to find the particular solution for this differential equation. Now find y sub p, the particular solution. To find y sub p, that y sub p depends on g of x. This is our g of x, right? G of x. We have to look at the classification for g of x. So to find y sub p, it depends on g of x, which here g of x is 2x squared minus 3x plus 6. Guys, this is not a solution. This is part of the differential equation. This is part of your equation. But we're going to use this to find y sub p, the particular solution. So since g is quadratic, quadratic. Our classification says, hey, if G is quadratic, your particular solution has a quadratic form. So our YP is AX squared plus BX plus C. But what is X? What is A? What is B? What is C? We need to find these missing values. Now, find A, B, C. It's a particular solution. It cannot have missing parameters. We cannot have A, B, C written this way. We need to associate numbers to A, B, and C. But how? Well, this is a solution for differential equation. It means that if I find the first derivative, second derivative, and third derivative, and look at my original differential equation, I can solve it. Yp prime is 2ax plus b. The second derivative of this possible particular solution is 2a. Substitute all. In the differential equation. My differential equation says, hey, I start by having the second derivative of y. The second derivative is 2a plus 4 times the first derivative, 2ax plus b, minus 2y, minus 2ax squared plus bx plus c. And on the right-hand side, I have 2x squared minus 3x plus 6. Okay, it's a simple equation, algebra equation. What do we have? You have 2a plus 4b minus 2c equals to 6. You have 8a minus 2b equals to negative 3. And finally, you have negative 2a equals to 2. Negative 2a equals to 2. So a is negative 1. I found my a. I'm going to substitute this guy here to find my b. So 2b is equal to negative 5. So b becomes negative 5 halves. And if I plug in a and b into the first equation, what do I get? I get negative 2 minus 10 minus 2c equals to 6. Or if you bring this guy back to the other side, c becomes negative 9. So the particular solution is also found y sub p. Y sub p is negative x squared minus 5 halves x minus 9. Okay, perfect. I found